Okay, so we left off here. I kind of went through this pretty quickly with the reduced variables. Talked about engineers really liking this sort of unitless temperature setup where they scale everything by the critical temperatures. And just here's an example of how that might work. And so the question would be, we did an automotive fuel exercise in the PChem 1 lab, our PChem 2 lab. But the point is here, at what temperature would hydrogen gas behave like hexane? So gasoline is really just a distillation cut out of crude oil. So there's a certain range of boiling points for gasoline. But hexane's a good model for that. So, you know, the properties of gasoline are very similar to the properties of hexane. And so if we were to want to be able to just use a hydrogen fuel, at what temperature, pressure would hydrogen behave like hexane, where we could just go and fill up our tank? And is it reasonable? Okay, so first of all, we think about what is the hexane reduced variables. We're at 1 atmosphere, and the critical pressure is 30 atmospheres for hexane. And we're at 298 temperature, and the critical temperature for hexane is 508 Kelvin. So the reduced temperature and pressure for hexane is 0.03 and 0.6. So those would be the unitless temperature and the unitless pressure for hexane at 1 atmosphere and room temperature. And so what temperature and pressure would hydrogen behave the same way? And so since we know the unitless temperature and pressure, we put those in with the critical constants of hydrogen, 13 atmospheres and 33 Kelvin, and figure out what the temperature and pressure would be. So we would have to be at 0.3 atmospheres and 19 Kelvin. So not practical. We're not going to be able to just use hydrogen as a liquid gas unless we were at half an atmosphere or less and 19 Kelvin. Okay, so that might work on the frozen moons of Jupiter, where we're probably not going to be driving our internal combustion engine cars, you know. But anyway, it was just an example of how to use reduced variables. Let's look now at a particular set of equations that I want you to be very familiar with, and that would be the Antoine equation and the Clausius-Clapeyron equations. So let's focus on vapor pressure and condensation. We've talked a little bit about equations of state. So the ideal gas law is the equation of state that you have in your mind. If we talk about state variables, we're talking about the number of moles or amount of substance, P, V, and T. And so those are your 4 state variables. PV equals nRT is the state variable equation, or the equation of state for an ideal gas. But the problem with that is that it doesn't allow condensation. So that's just the ideal gas law, so it's only going to be useful as an equation of state for ideal gases. You can correct those equations of state, and there are many. Okay, this one is familiar, perhaps you've heard of it, the van der Waals equation of state. And if we write the equation of state in terms of pressure, so pressure equals nRT over V, we can correct that term. And so if you think about the properties of an ideal gas, if we say that the particles have no volume, then the volume of the room is the full volume that particle has to move around in. But what if the particles do take up space? Okay, then you need to reduce the amount of volume by a little bit. So the volume effect of the particles actually being, having a volume should be reduced from the volume of the room. So we see that correction in the denominator up there in red. So we're subtracting some correction term from the volume based on the volume of the particles. And it would make sense that should be scaled by the number of moles. So if you have more moles of gas, then you're going to subtract more from the volume of the room. Now that's also called a repulsive effect, okay, because if you shrink the volume of the room, what's actually happening, that the pressure is going up because the molecules are banging into each other actually more often than they would if they didn't have any volume at all. So because you're increasing the collisional cross-section of the atoms or molecules, you're actually raising the pressure. You're shrinking the denominator, which causes the pressure to go up. And so that B term in the van der Waals equation of state is called the repulsive term. I talk about it as a reduction of volume, but you can imagine it causes the pressure to go up, so that's a repulsive behavior. Okay, does everybody follow that mentally? Yeah. Okay, now there's also an attractive term, right? Think about the 612, the Lennard-Jones 612 potential. The attractive region causes those molecules to stick to each other or be attracted to each other. And we're measuring the pressure at the wall of the container. So the pressure should drop if the molecules are attracted to each other, especially if they have sort of some floppy character to them. Whereas if you have a collision and it excites the vibrations, that energy, the translational energy is lost and the vibrational energy goes up. So the molecules are able to store energy in themselves. That's heat capacity. And so if you think about the vibrations and rotations of the molecule, translational motion can be turned into other motion. And so you have two molecules come, they collide, and then they distribute that energy and they come away very slowly. And then they hit the wall with less energy, so the pressure goes down. And so the attractive term over there has a minus sign in front of it. That A piece is attractive. And of course it's going to be scaled, by the number of moles. It's scaled by the number of moles squared and divided by the volume squared. So essentially that's a density term, the number of moles per volume. So we have an attractive term that lowers the pressure. We have a repulsive term that raises the pressure. And those are corrections to the van der Waals equation of state. But the downside of the van der Waals equation of state is it's still really a gas phase equation of state because it has some unreal properties here in the middle. So notice if we're coming along, I'll just walk you through this. If we're coming along this isotherm here, and I'm compressing the gas and the pressure goes up. So think about it. I'm pushing on a piston, compressing the gas, the pressure's going up. That's what you expect. But we get to this point here and I'm still compressing the gas and the pressure goes down. You ever experienced that on a bicycle pump? You're pushing down and it's getting more and more pressure and then all of a sudden it sucks down. That never happens. That's not realistic behavior. So the van der Waals equation, these loops in the van der Waals equation are not realistic. So when you get to the places where condensation would occur, the van der Waals equation of state breaks down. And so we've drawn this line across here. This is actually what we call the Maxwell construction. So Maxwell tried to fix this equation of state by drawing a line across here where these two volumes in yellow equal each other. And so he said, what if we correct this van der Waals equation even further and we draw a line here, and that would be the vapor pressure. P vapor. And where do we draw that vapor pressure line? We draw it so that the yellow regions equal each other. And that way the van der Waals equation at least looks realistic. It's a great concept to correct this equation sort of with the sort of Boolean logic, if this area is equal to that area, then draw the line to where they're equal. But it doesn't really give you accurate vapor pressures. We kind of show this in the PChem 2 lab for the undergrads where they do this in Excel. So they draw that line and they move it around with solver until those areas equal each other, and then they look at the vapor pressures, and the vapor pressures are really not very good. But at least the concept is a great idea to try to correct this equation. It does give us that PV curve where you have the compressibility of the gas. Let's see if I mark compressibility of the gas here. You have the solid, the constant vapor pressure when you have the gas in equilibrium with the liquid, and then you have the compressibility of the liquid here. So this is all liquid and it's repulsive. This is all gas, and it's compressible. And then you have the vapor pressure at all these regions in between. So. Now, if we took the the volume and divided by the critical volume and the temperature and divided by the critical temperature, those would be the reduced variables. And this is the van der Waals equation of state corrected with those reducible
temperature variables.
So let's focus now on these vapor pressure curves. This is the Clausius-Clapeyron equation. And so we're dealing with the vapor pressure at two temperatures. Now this is fantastic. We have a star on the pressure and temperature. Those will be your reference pressure temperature values. Now, if you're trying to figure out the vapor pressure of a substance at a given temperature, how would you do that? What do you need? Well, you need something related to the vapor pressure of that substance. And so what is happening when a substance's vapor pressure equals 1 atmosphere? So if we take water, we have a vapor pressure above the water, and what happens to that liquid when its vapor pressure is equal to 1 atmosphere? It's boiling, yes. So typically at the bottom of the pot where the heat source is, the vapor pressure is a little bit higher than 1 atmosphere. It creates a cavity. We call it a bubble, but it's really a cavity, okay, filled with vapor. And then as it comes up, as it cools, the vapor pressure drops down and the cavity collapses. And so when you're warming a pot of water, you start to see these cavities form and collapse and so on. But when the vapor pressure is 1 atmosphere and the temperature is the boiling temperature, then that cavity can maintain its cavity nature all the way to the top, and we call it a bubble, but it's really a cavity. Those cavities come all the way to the surface and they pop and release the vapor pressure. So we call that boiling. And if it's at 1 atmosphere, that's the normal boiling point. So 1 atmosphere is the normal boiling point for a substance. And you can look those up. So the normal boiling points for substances, we know the pressure is 1 atmosphere. And so typically the temperatures are listed, and that's all that you get. So you can look up the boiling point of a substance, you get the temperature, but the normal boiling point also implies that the pressure at that temperature is 1 atmosphere. So those are your two starred values, P star and T star. So T star is the boiling point, P star is 1 atmosphere. And then you can put any other temperature pressure in there, and you can solve for the new vapor pressure if you have the enthalpy of vaporization. And so that's the thing that you need to look up, is the enthalpy of vaporization for that substance. So if you know the enthalpy of vaporization and the boiling temperature, you can find the vapor pressure for that substance. I do like to teach this equation because this is one of the few equations that I had in PChem that I actually used in industry. Because what kind of situations would you use this equation in a regular lab situation? So let's discuss that. Why would this equation be so useful for industry?
Some of the properties of whatever chemicals you're dealing with.
A property of chemicals you're dealing with, so that's good. Someone extend on that. So it's like you want to know the properties of the chemicals you're dealing with. What kind of properties? Someone else. What kind of properties do you want to know about?
I was thinking the temperature where you're not, like I was thinking in a solvent situation, not losing my solvent, but still being able to heat it to a point that I'm generating a vapor without, losing it.
You can kind of calculate how much you're going to lose, how much is going to be in the vapor phase. Yes, yes. So you could learn more about your reactions if you knew more about the vapor pressure situations. Oh, and that's also why we put refluxers or condensers on our apparatus, because you've got a lot of vapor pressure. When you got toluene at an elevated temperature, it would just boil dry. But you put that condenser on top and you drop that vapor pressure down and it condenses and it drips back down into the flask. So we're sort of maintaining our solvent by using that condenser. But there's more of a, let's see, how do I want to say this? It's less of a chemical reason why you want to know the properties of the solvents that you're dealing with. And it's mostly solvents.
When I think of pressure, I think explosion, if it's too high.
Okay, yes, definitely. You would want to know, gee, is that temperature going to be higher than my glassware, right? So I could look at, we wanted to do liquid ammonia. It was 10 atmospheres at room temperature. That's the vapor pressure above liquid ammonia, 10 atmospheres at room temperature. That's a really scary thing to put in glassware. I certainly wouldn't use a regular organic kit for that. okay, and seal it up so that I didn't lose my ammonia. I'd be, essentially at room temperature heating a closed system and blow up the glassware. So I'd have to have, it would change what kind of apparatus I use. But again, that's still focused on the reaction that I'm doing. The reason in industry that we focused on the properties of solvents was for personnel exposure. Okay, so to know, if you know the vapor pressure of that substance, and let's say let's make this easy. Let's say it's 0.1 atmospheres. Okay, so we've got a solvent that's pretty volatile. The vapor pressure above that liquid at room temperature is going to be 0.1 atmospheres. Okay, what does that mean if it comes to equilibrium in the room? Like the door is shut for quite a while, say it's in the stock room, and the bottle got left open, and now I've got 0.1 atmospheres of that solvent in the room. That's 10% by volume. A lot of the personnel exposure numbers are in the ppm, like 200 ppm, 400 ppm, parts per million. Okay, yeah, so we're 4 orders of magnitude above that at 10%. So you're getting 10,000 times more vapor exposure than if you were allowed to be exposed to 100 parts per million of that solvent, then you're being exposed to quite a bit more, many times more. And so this was the calculation that we needed to do on various solvents to see if personnel could work safely with the lid off, or do they need to work in a hood? If the thing's not very volatile, you don't have to work in a hood. But if it's very volatile, you need to protect yourself and work in a hood. If you can't work in a hood, you need to wear a respirator. And so these are decisions that you make when you're working with these chemical substances, and this equation is very, very useful for figuring out what your exposure is going to be. Okay. Now you're probably not going to reach equilibrium because you need a static space without AC, without filtered air or anything like that. But that's the worst case scenario. So if you've got an open beaker of benzene in this room, the worst case is if it all came to equilibrium in the room and then you walked in and you were exposed, you would be way over your permissible exposure limit. So all of those kinds of exposure limits are listed on safety data sheets. But how do you calculate them? First, you have to calculate the vapor pressure and then kind of do the Dalton's law of partial pressures to see what the parts per million are or the parts per thousand. Okay. So there's other reference points. So all you really need is a temperature pressure pair. The normal boiling point is the easiest to find typically, but you also have triple points. So you could use a triple point. Any temperature pressure pair can be used in this equation. You can also use the critical points. So if you have the critical points, if you're going to be working with this substance at really high temperature, it's probably more accurate in that region to use the critical point. But it's pretty amazing that if you plot the log of pressure, and I did this relative to the triple point for water, and then plotted on there the boiling point, and plotted on there the critical point for water. And so we're going from 273 to 650 degrees, and it's pretty linear. So that tells you that the enthalpy of vaporization is pretty constant for water from its triple point all the way up to its critical point. And so if you use this equation, you're going to be pretty accurate for the vapor pressure of water for, from 270 all the way up to 650 degrees. So that's pretty amazing that you could calculate the vapor pressure of water at all of those different temperatures and pressures. Okay. And so here's another equation, the Antoine equation. You'll see Antoine coefficients or Antoine constants for various substances in the CRC. And so down here at the bottom, it's the log base 10 of pressure is equal to A minus B over T plus C. And so you'll have AA, AB, and AC listed in a lot of databases. And AA is Antoine A coefficient, AB is Antoine B coefficient, and AC is Antoine C coefficient. And you just put them in that Antoine equation. And these are just empirical fits to the experimental vapor pressure curve. And so if you can't find the enthalpy of vaporization, a lot of times you have the boiling point and you can't find the enthalpy of vaporization. You've looked in the CRC, you've looked online, Wikipedia doesn't have it. You looked everywhere, okay? How are you gonna calculate your vapor pressure? Well, you might find the Antoine coefficient. So that's a second route, a second way to calculate those vapor pressures for that substance. All you need is the temperature and you can get the pressure. So that'd be a great, using those two, find examples for those, great calculation to do for the classic problems for the discussion board. And so I think, I keep forgetting to start a brand new thread. So whoever goes on there next for the discussion board, if you'd start a new thread of classic problems just for this middle part of the course. Yeah. You posted in the same one. Maybe we can move it. I don't know if you can move it, but go ahead, if you'll start a new, maybe a new forum, and then put a new thread in that. So that way it's easier to sort through all the problems if we have a new forum coming up. Yeah. If you can't start a new forum and you're ready to do it, shoot me an email and I'll do it, and then you can post it. Okay, thank you. Do these match? Yeah, they're pretty close. I mean, one is using the Antoine equation, one is using the Clausius-Clapeyron equation. So. Let's get back to our phase diagrams.